Okay, then I guess we will start now. So good day, everybody. It is a great pleasure to welcome all of you to another installment of our Responsible AI seminar. My name is Eike Petersen. I'm a postdoctoral researcher in a project on bias and fairness in medicine at DTU Compute. And the seminar series has been initiated by my collaborators, Melanie Ganz, Åsa Verhagen, and Sune Holm. And I now have the pleasure to continue organizing it together with them. So before I begin, I'd like to inform everybody that this meeting is being recorded. So please be aware of this, and we will make it available afterwards on YouTube and on our website. Today, we are extremely happy to welcome Ben Glocker. Ben is a reader in machine learning for imaging at the Department of Computing at Imperial College London, where he co-leads the biomedical image analysis group. He holds a PhD from TU Munich and was a postdoc at Microsoft and a research fellow at the University of Cambridge. He is a member of the AI task group of the UK National Screening Committee, advising the government on questions around clinical deployment of AI for screening programs. His research is at the intersection of medical imaging and AI, aiming to build computational tools for improving image-based detection and diagnosis of disease. Ben, we're extremely happy to welcome you with us today. Please, the stage is yours.
Thank you so much, Eike, and thanks a lot to the organizers for the invitation and the opportunity to share some of our thoughts and recent work, which I hope fits well into the scope of this seminar. So let me share my screen.
I'm very sure of that.
We'll see. So this is so some disclosures beforehand before I actually start. This is very recent work, and it's ongoing work in a sense that if you check out our archive paper, this is already version 4 within a couple of months. And the reason is because it continues to develop, and it does make us think about a lot of things and question a lot of things that we thought are true at some point, and then we realize they are not at another. So I very much welcome any criticism, any challenges, any questions at the end, but even during the talk. If something is very unclear, please do feel free to interrupt me. So I will try to tell you a little bit what we did. So the official disclosures, I do have some industry roles as well. They shouldn't affect at all what I'm talking today about today. I have my Imperial hat on today, so I speak as an academic, as a researcher working on that project. I'm not alone. I've done this work together with Charlie, Melanie, and Stefan, all members of my team at Imperial. And as you might have already seen in the announcement, there's a preprint available, so feel free to check that out. It might have a few more details than what I can cover here in the talk. What I'm reasonably proud of is that I think it's one of those rare works where I believe everything I will show you is fully reproducible. So you can check out the code, it's on GitHub. And the data we have been using for the investigation is publicly available. So you should be able, with almost like a click of a button or running a Python script, to fully reproduce what I'm showing you. So to set the scene, I want to start by just discussing a little bit of why are we looking into this. So give a bit of motivation where this fits into the broader scope of using machine learning for image-based predictions. And I guess if we look at how we have done things traditionally before the deep learning era, was where we typically try to develop models or build models that would take a almost predefined, or sometimes it's called hand-engineered, set of features that can be either directly extracted from images or some other, for instance, clinical information that you might give to a model. And that information is then used for a learning-based prediction model. So you, for instance, have a logistic regression or some other linear model that takes a set of features, learns how to combine them, and makes some output predictions. The nice thing about these models is that we have full control about the set of features that we give to the model. And often that means that those features are interpretable, they have semantic meaning. When we look at the more modern ways of doing image-based prediction, these would typically relate to approaches where we use things like deep neural networks. right? So here the idea is that we are actually not predefining what type of features are being used or extracted from the images, but instead we use what we sometimes call a neural network backbone, which typically is using convolutional layers for feature extraction and some non-linearities, so that we learn basically from a given input image a non-linear transformation into what we then would call a feature representation. This is typically, so this is just a schematic here, but and a simplified way of looking at neural networks. But you can think of it basically mapping a high dimensional input like an image into a lower dimensional feature representation, which typically sits at this penultimate layer of the neural network. And then this layer or this feature representation is given to a simpler model, typically again more something that would resemble a linear model, something like a logistic regression again, that would combine the features extracted automatically from the images to make final predictions. And I think it's sometimes useful to use this this schematic here, because it allows us to think a little bit further about what happens at what stage. And in particular, when we think about how does a model make a decision, what information is a model using, we can think about where that information is stored and when is the decision made, what information is actually being used when we make predictions. Now, there are lots of examples in the literature of showing that these type of approaches of using deep neural networks are very successful. We see lots of promising performance in various applications, whether it's semantic segmentation, for instance, brain lesion analysis, direct prediction of diagnosis, for instance, in retinal disease. We have seen early adoptions of deep learning in skin lesion classification, and of course, other applications like breast cancer. So a lot of reports and clinical trials even showing that it seems this type of methodology or model is performing really well in terms of accuracy. And what we or many others now start to think about is, okay, so what are the possible risks and what's the possible danger of using these maybe sometimes perceived black box type algorithms. And there's an increasing number of reports that raise very rightfully concerns about that these type of algorithms might amplify biases because they are based on training on historic data. And we know that historic data always contains certain biases. So maybe if we are not anymore in full control of what features are being used, how can we make sure that not unwanted features are being used within these kind of black box algorithms? So if we think about an example application, which I will use throughout the talk now, and this is the application we also used in the paper, which is chest X-ray disease detection. We want to illustrate a little bit why these concerns might be justified, and what can we do about them. So the example application is we have chest X-ray and we want to predict the presence of disease. So this would be our model. And we say that the neural network backbone is basically extracting the disease-related features. And then we have the prediction layer, which makes the final decisions, which features exactly to use in order to predict whether the disease is present or not. We've been using, as I mentioned, a publicly available data set. So we use Checkspert for the following results, but similar can be done on other data sets. We also have some preliminary results on Mimic, for example. This is another large chest X-ray data set that we can use. The nice thing about these data sets is that they, first of all, are reasonably large. So they have thousands, up to 100,000 or 200,000 scans that we can use, which is good. We know these deep neural networks are data hungry. So that is one of the checkboxes. We have a large data set that we can use, but also they come with additional meta information about the patient. So Checkspert in particular has now the full demographic information about or some of the demographic information of the patients being released, including protective characteristics like biological sex, self-reported racial identity, I think some of these data sets even have insurance status and other things that people have looked at. Together, of course, with the diagnostic labels. Now, if we take an out-of-the-box deep neural network, any architecture you can think of that is probably suitable for this, whether it's a DenseNet or a ResNet or even a VGG, if you train it, for instance, on the Checkspert data set to do disease detection. So keep in mind in Checkspert there are 14 different labels. So typically this is posed as a multi-label problem rather than a multi-class problem, because some of those labels can be, they're not all mutually exclusive. But here for the purpose of this work, we will only focus on two specific labels that are present among those 14, which one of them is the no finding label, which basically kind of represents whether there's any disease present, right? So if it's a no finding, it's mutually exclusive of all the others, saying none of the other conditions has been detected in that scan. And then we look at one other disease label, pleural effusion, mainly for the reason because it is mutually exclusive with no finding, which helps us a little bit with our investigation, but also it has a different statistics, different characteristics in the population. It has a very different prevalence than no finding. So it also gives us a bit of a complementary thing to look at. But the important thing to note here is if you train, as I said, an out-of-the-box model, what you will see is disparities in these disease detection models. So if we now break down the performance for detecting whether the no finding is true or false, or there is pleural effusion present in the scan, if we look at the performance in subgroups, we do see differences. And this has been remarked in published work. So that, for example, there's the work by Sayed Kalantari, associating this behavior, for instance, that we see here, that one of the subgroups, so these are the patients that self-identified as Black, there's an increased false positive rate compared to the other subgroups for the no finding label. And that basically means that no finding is predicted more often for that subgroup, but incorrectly, right? So this is why some people associate this with underdiagnosis bias. It's a bit more complicated if you actually look into what's exactly happening there, but you certainly do see these disparities. And these disparities give rise to concern, because it basically means that training these models on these large data sets does not necessarily mean that they perform similarly well, or in general that they perform similar. Whether it's well or worse is a different question, but that there are disparities in subgroups. Now note here, this is important later for the discussion, that the AUCs are not that different, or actually are very stable across subgroups. So AUC basically just measures the general discriminative power of the model for making the classification. But then if we have to choose an operating point, so at some point you have to choose a threshold at which you say, what is your sensitivity specificity? So in this case, we choose a global threshold that is optimized for giving a 0.2 false positive rate, that this threshold then doesn't generalize to all subgroups. Now, these disparities that you can replicate this when you train your own models are concerning, in particular when you think about another aspect, and there are some other works that have shown this, and we replicated this, so this is all reproducible, is that these networks can also predict protected characteristics. And some of them are quite surprising. So for instance, you can do biological sex classification on chest X-ray almost perfectly, very high accuracy. A recent work where there is a preprint available called Reading Race have shown that you can also predict the self-reported racial identity with a very high accuracy. So a network specifically trained for predicting a protected characteristic has very high accuracy. Now, if you combine these two observations, right, so there are disparities across subgroups, and a model can predict protective characteristics. If you combine the two, this might raise concerns in a way that maybe the model has learned to identify whether a patient belongs to a certain subgroup and then behaves very differently, for instance, resulting in the different performance that we saw earlier. And of course, that is concerning, because we might have reasons to say that certain diseases should be predicted independently of whether a patient would identify to be part of the white, Asian, or Black population. And maybe same for certain diseases regarding biological sex. So there's the general question of, did the models use information about protective characteristics when making predictions? It's important to keep in mind that when you look, even before you train anything, if you just look at the data characteristics, so here we are looking at Checkspert, at the set of Checkspert images that we use for this analysis, that there are already a lot of differences in the subgroups. And this has many reasons, and we can discuss at length what are the possible causes for these differences. Of course, there's sample selection bias and all kinds of issues that might occur just because of the data collection. But there might be also general differences in the subgroups. And of course, there might be biases due to, for instance, certain subgroups having poorer access to healthcare, systemic racism in healthcare, and all kinds of other reasons why we might see just statistically differences in these subgroups. Now, if this is our training data, just to point out a few here, a few important differences is, first we see, if we look at the overall age distribution, that for some reason the subgroup of the patients self-identifying as Black is almost 10 years younger than the white patients. We don't know exactly why. The Checkspert dataset description doesn't explain where these differences come from, but these are differences that we can observe. Now, the other very obvious skew in the data is that the large majority of patients is white. 78% of the patients in the dataset is white. Now, the combination of different things here could also greatly contribute to disparities that we see in the model performance. So, for example, if we look at pleural effusion, the prevalence of pleural effusion is almost 10% lower in the group of Black patients. Now, this might have to do with that they are younger, because younger patients typically have less disease. And we see this again if we look at the age distribution over the different disease labels. So it's important to keep in mind that these differences are in the data set. And now the big question is, if we train a model for predicting disease, would that model know about these differences? Does it use even these differences? Given that we know a model can, for instance, predict the racial identity and the biological sex of the subject. So this is the big question that we try to shed some light on it. We'll see how successful we were with that. But one way of doing this, and this is not something that we came up with, but for instance, in the Reading Race paper, people looked at this, what we then called the supervised prediction layer information test, just to give it a nice name. So this is the split test that you can use, which is basically following the simple idea of using transfer learning. So you take your model that has been trained for disease detection, and then you replace the prediction head, right? So if I go forth and back, you see basically I'm keeping the neural network backbone that has learned to extract disease relevant features. And I'm adding a new prediction head here. So I'm just replacing that simple model here at the end and say, now I want to predict biological sex, or I want to predict racial identity, but using the features that have been learned for disease detection. Now, how well does this work? So the split results are summarized here. If we take the model that I just showed you with all its disparities and performances on detecting no finding on pleural effusion, these are the AUCs you get for predicting biological sex and racial identity. At the lowest row, I show you what a model is capable of doing if it's directly trained for these prediction tasks. So it learns task-specific features, right? And all the numbers above these lines are basically using the backbone of the disease features or other features, as we will see. So it's important to keep in mind, if we look at these numbers, so if we look at these AUCs for doing that task, on their own, they are not very informative. So we need to have some baseline comparisons. So one thing we can do, we can just say, oh, we don't use disease features. We just use randomly initialized convolutional layers here. So we would call them random features. They are basically random projections of the input data onto a feature vector. And then it's basically up to that model to use these random projections to make a decision. What is interesting, it's far better than chance. So even such a model can do, to some degree, predict racial identity and biological sex. Now, if we take ImageNet features, for example, which are completely unrelated to disease, they are even completely unrelated to X-rays. They have never seen an X-ray image when being trained for ImageNet classification. What is interesting is that the AUCs we get here are quite similar to the ones we get when we use disease features. Now, this is interesting because, remember, our question was basically if a disease detection model is capable of afterwards predicting racial identity and sex, we might conclude that the disease features have learned race-specific and sex-specific features. But if we get similar AUCs by just using, for instance, ImageNet features, we might wonder, maybe the disease features are actually not necessarily encoding racial identity and sex. But we cannot be sure about this. Here's another example where we use a disease detection model that has been only trained on a subset of the patients. So here we use specifically male patients and white patients only because they were always the majority class. So just to make sure that the disease features have seen a reasonable number of subjects. But again, here the interesting thing is that these features that have been learned for these disease detection models have never seen the variation of biological sex and racial identity. And still, the prediction layer, specifically then trained for sex prediction and race prediction, gets similar AUCs. So again, that raises a bit of the question, is split a useful test to check whether the features that have been learned are predictive or even meaningful for a secondary task like race and sex classification? So what we concluded from this is that a positive split result, so saying that you get a high AUC, is a good test to see if it's predictive, but it's not a sufficient test. It doesn't mean necessarily that the features are biased or directly that the disease model has learned or even made use of the protective characteristics. We cannot say this for sure, given these results, that we get similar results on ImageNet and these biased models. So that kept us thinking a little bit about what are actually the relationships between prediction tasks. And we try to kind of illustrate this with some schematics here to highlight what could possibly happen in these models. So on the most left, we basically see an example. So the setup here is that we have two prediction tasks. One of them is we want to predict the color, and the other one is we want to predict the shapes, right? So we have crosses and circles, and we have orange and blue. So these could be two prediction tasks. Now, if we have samples that have basically just two features, x1 and x2, and we want to do one of the tasks well, then we see that we can be in different scenarios, as we call them. So in scenario A, we basically say that the tasks are completely unrelated. And also the features are unrelated. So it's unrelated both in the output and in the input, meaning that if we want to do color classification, right, we can just rely on feature x1. If we want to do shape classification, we can just rely on feature x2. And if we solve one of the tasks, we cannot solve the other one, right? So that would be complete unrelation between the two tasks. let's first talk about scenario C. So scenario C might happen when the two tasks are very strongly related, both in the input and in the output space. And I mean, this is an extreme scenario. Obviously, typically there would be some degree of correlation maybe between tasks, not as strong as shown here, but this just to illustrate. So in this, you cannot solve one task without solving the other. Right? So if you solve it for color classification, you automatically solve also the shape classification. Now, the interesting thing, I believe, is scenario B, because it's somewhat similar to scenario C in a way that we cannot just rely on one feature. So we cannot just use X1 or X2 to solve either of the tasks. We have to use both of them. But still, we are not solving the other task, even if we use the features that are useful for solving both tasks. So what I mean is, if we want to solve the color classification, we have to use a combination of X1 and X2 in this case to get that decision boundary. But if we want to use the shape classification, we also have to use X1 and X2. But you can see that if you afterwards would project down the samples just on the discriminative subspace, you're not solving the other task. So it means that there are scenarios in the real world, illustrated with this toy example, where the features are useful for both tasks, but it doesn't mean the tasks are directly related. So that is what we try to illustrate. I hope this is clear. We can maybe come back to this if it wasn't that clear. So the question now for us was, okay, so how could we otherwise check whether the tasks are related in a way that it's potentially harmful? And one way of checking whether tasks are related is to do multitask learning. So multitask learning is a standard machine learning approach to solve multiple tasks at the same time with a single model. And what we would do here is we would basically have a shared feature representation and we would add multiple prediction heads. So now my code is coming through slowly, but we'll see how it goes. So here we're adding multiple prediction heads at the same time. So we're solving with a single model the disease detection, the sex prediction, the race prediction. And we can optimize this jointly. So this feature space now should be discriminative for all three tasks. And I think it's quite interesting then to look at those features and how they relate to each other given those three tasks. Now, the first thing is we can look at the performance of such a model. And what we do see is that the model has similar disparities as the one before. It actually has increased even the disparities that we saw earlier, if we compare that to the single task. So if I go forward and back here, on the most left, you see the previous rock curves for disease detection for the two conditions, no finding, pleural effusion. So there's a larger disparity for the multitask model here even. The multitask model itself has very well learned sex classification, reasonably well race classification, almost as well as the model that just starts race classification. And disease still is similar in terms of AUC and performance, but the disparities are still there. So for us, this was a way to check whether if you give as a supervision the protective characteristics, you might expect that if the model can exploit that information, should it perform maybe even better when you give those labels compared to the single task model? It didn't perform better for sure. But there's another thing that's interesting about this is that we can do model inspection now. And I think this is probably the most questionable part of that study and maybe debatable, but we can have a look, because this comes down to interpretation to some degree. But basically what we do in model inspection is, and this is why this schematic is useful, I believe, to think about where are the task-specific features and where are the final decisions being made, is that we can look at those separately. So let's first have a look what we mean by model inspection when we inspect the prediction layer. So remember, this is something like a logistic regression, which basically produces weights on these penultimate layer features and then makes final predictions. The output of the prediction layers are sometimes called logits. I know it's not the fully appropriate term for it, but let's keep them called logits, or raw scores, prediction scores, before we pass them through some other function to just get pseudo probabilities. But they are very useful to look at, I believe. And here comes the reason again why we're just looking at two labels, so plural diffusion and no finding, because it allows us to produce 2D plots that we can look at. And as I said earlier, they are mutually exclusive. So what's interesting also is that they produce clusters that are basically separating from each other. So let's talk through what we are looking at here. So this is the single task model I showed earlier, which has disparities in subgroups. And now what we can do is we look at these raw logits, right? For each condition, we get a logit that would then be maybe passed through a sigmoid function. But if we plot them here in these scatter plots, so what we did here is we took from each group, we took 1,000 samples. And if we look at those outputs, what we see is for the disease label, so if we overlay with color for each sample to which condition it belongs to, we see this nice clustering as we would expect for subjects that have plural diffusion, for subjects that have no finding, and subjects that have other. Just a second. And if we now overlay other characteristics, like for instance, the demographic information or age or racial identity, we don't see these clusterings that we might expect or might expect if the model is very biased and does different things for different subgroups. So we do see it for age, and that makes sense, right? So the younger patients are around the cluster of the no finding label, and the older subjects are more like all over the place. But we don't see very clear or no obvious separation, for instance, on biological sex, and not so much separation on racial identity. There's a little bit of shift in the marginal distributions here. And that shift actually explains, or it shows why there is a disparity in the false positive rate. Because if your logits are slightly shifted, it means your threshold needs to be put at a different place to get the same TPR value. So it's not entirely clear where that shift here is coming from. We can discuss this later, but there is no clear clustering. So that's the good news. We don't see that the model is clearly identifying whether a subject is male or female or white, Asian, or black, and then possibly even makes a different decision for the subjects. So that is one way of looking at the models. If we now compare this to the multitask model, we don't see major differences. And that is quite interesting, right? So we are looking at the outputs with respect to disease, but the model has in its features also learned to clearly separate sex and racial identity. So if we don't see a major difference between the multitask and the single task model on the output of disease, it might mean that giving the labels of biological sex and racial identity here doesn't seem to have a big effect on the outputs of disease labels. That might be good news. We will have a look at this again. So this is the inspection of the prediction layer. Now the other inspection we can do is on this feature representation, the penultimate layer that I mentioned earlier. Now this is a little bit more complicated because these feature vectors are typically high dimensional. So in a typical neural network, it might be 512 dimensions or 1024. I think here we use the DenseNet. So I think it has 1,000 dimensions for these features. So we have to use dimensionality reduction to look at the feature embeddings. You can use things like t-SNE, for example. So this is t-SNE on top of PCA to give some stability. I know there's a lot of criticism about t-SNE, but I think t-SNE is actually quite useful for this purpose. So again, what t-SNE allows us to do is what are the features and how are they clustered across the samples? How are they distributed across the samples? So if we look at the t-SNE, first two t-SNE dimensions here, again, we see a good clustering in feature space regarding disease labels. That makes a lot of sense. no differences between males and females. They're equally like clustered, distributed in the feature space, which I guess is good news. The age, of course, has a bit of clustering. Again, we see the subjects, the younger patients, being more distributed around or more clustered around the area of no finding, and really not much differences in terms of racial identity in the feature space in the single task model. So again, this maybe gives us some confidence or some assurance that in the single task model, even if we know that protected characteristics in this example of Checkspert can be predicted, it seems the model doesn't pick that up when it does disease detection. Now, how does the multitask model look like? And I think this is quite interesting. So first of all, we still see a clustering for disease. That's good, right? So the multitask model had a similar performance for disease prediction. Sex is very well clustered. Remember that we can very well predict with high accuracy male and female characteristics. And that basically means that the model has completely separated those two groups in the feature space. For age, now basically what it means that we have two subspaces here, right? So there's really a space for the male and the female subjects. And also what we see is that racial identity, because it was a supervised label to be used in multitask, has of course an effect on the feature embeddings. Now here we come to the limit of t-SNE a little bit. So we also look not only at t-SNE, but at PCA. And PCA is interesting in this case because PCA by construction will separate that high dimensional space into orthogonal vectors of largest variation. And orthogonal means they are independent of each other. So if we look at PCA mode 1 and all the variation that happens along that mode will be orthogonal to PCA mode 2 and then orthogonal again to PCA mode 3 and 4 and so on. So again, interesting, first looking at the single task model, we see PCA mode 1 as expected is separating disease, right? The model has only seen disease labels. So very well visible here, the variation of the samples along PCA mode 1, all very much relating to disease, and not so much other information in the other PCA modes. So it's all really captured in the largest mode of variation mostly. No differences in biological sex. Apparently very little or almost no differences regarding racial identity. PCA mode 4 and 3, you really don't see much either. So just as a confirmation to have a look at those further modes. Now, the multitask model is interesting, I believe, in this context. And I think that is why the multitask experiment is useful as an additional check whether the protected characteristics may or may not be used. Is we see something interesting which relates back to our toy example with the sample, with the three scenarios of classifying color and shape. What we do see now is so sex is dominating the prediction task and the feature space. You can see now PCA mode 1, which was previously disease, is now biological sex separation very clearly. In PCA mode 2, we see the separation of disease. So remember, these are orthogonal modes, but most of the separation for disease is happening in PCA mode 2, apparently. PCA mode 1, biological sex. Not so much differences, a bit of differences here in the marginal distributions again, in the different subgroups again. Right? If you look at the males and the females, there seems to be a separation within the male group. But most discriminative variation is in PCA modes 3 and 4 combined when we look at racial identity. And again, that might give us some assurance that racial identity, even in the multitask model where it's given, plus biological sex, plus disease, they are encoded, and that I guess relates to the title of the work, algorithmic encoding, are encoded in different subspaces. And that may or may not indicate that they are actually not useful to each other when doing the tasks, but they can use the same set of features when you predict them. So that is going back to the idea of there is a scenario B, where we might be able to predict protective characteristics from features that have been learned for a primary task like disease detection. But maybe the good news is that it doesn't mean the model has necessarily picked them up. Now, does this mean it's all good? It's not. So what we did see is that for this specific example, with the model inspection and the multitask experiments we have looked at, we have maybe some hope or some assurances that the model has not used protective characteristics when making disease detection predictions. However, the model can use characteristics, and we will have a look at this. But we also need to look at more generally again at the disparities. They were still true, right? So there were clear disparities in the subgroups. So where do these disparities come from? And I think that is a hopefully interesting discussion we can have, is that if you go back to the patient characteristics, the population characteristics, there were clear differences, for instance, in the prevalence, in the population shift. You had a large majority of white patients. And we do have generalization issues with these models because of the imbalances we have in the data. The models don't generalize to these subgroups. It doesn't mean the models actually explicitly use the characteristic information, protect the characteristics, but it still means that the models are not quite generalizable across subgroups when you use these fixed operating points. So we did this, for instance, by looking at models that are trained on all patients, just white patients and all, just male patients, where you can exacerbate some of those disparities. Now, the protective characteristics will be used when there is a signal in the data that would make the model to want to use them when the optimization is being done. And we have looked at this by explicitly perturbing some of the data. So we wanted to understand what is happening if we explicitly introduce some perturbations. For instance, if we introduce label noise, and again, so we have chosen here the subgroups that were in the minority always, because we wanted to see what is happening with the underrepresented groups, because that is of most concern. What happens if you introduce, for instance, in the labels, some noise where you randomly flip the disease labels? And if you do this, for instance, for 50% of the Black patients in the training set, and we don't touch the test set here. The test set has still exactly the same labels as before. We just do it on the training set. What happens is that you suddenly see very largely disparate performance, not just in the TPR and FPR shifts, but also in the AUC. So here clearly the model has an incentive, a bad incentive to realize whether a subject is of a certain group, because then it can deal differently with the introduced label noise. So the same can happen here with the female patients. When we just introduce 10% of female patients with label noise, the model will pick this up. And interestingly, you are not just seeing that in these performance metrics, but you see it in these model inspections that I showed earlier. So what's now happening is, so for instance, in the label noise with 50%, where 50% of the Black patients have label noise, you, again, if you look at the output, the logit outputs of the disease prediction layer, you see a clustering happening very clearly here. So actually the model, and this is on the test data, right? So these are the predictions on the test set. So only the training set was perturbed, but what it means that the model is now using the information that it can isolate a subgroup, and then it learns a separate mechanism for predicting disease for these subgroups. So you see these clear clusterings happening here for the Black patients, both in the logit space and in the feature space. Same with the female patient, because male-female prediction is even easier than the racial identity in terms of predictive accuracy. You see an even heavier clustering here. So the model, by just giving 10% of the female patients label noise, the model is now starting to separate the two groups and learn separate disease mechanisms. So you have a disease mechanism in logit space somewhere here for the females and here for the males. And you see this very clearly in the clustering effect, both in the logit space and in the feature embeddings. Good, so this brings me to my conclusion. So I think the risk that protected characteristics may be used is very real. And this can happen in particular with this. I mean, this was a simulation with label noise, but this is what might happen in the real world, right? So we do know that certain subgroups have, for instance, poorer access to healthcare. So their labels in the historic data might be more noisy, might be even incorrect, might sometimes maybe even deliberately incorrect due to systemic racism. So there might be underdiagnosis, overdiagnosis, all kinds of effects on the data that we use for training machine learning models that might have an effect on the way this information is being encoded in these models. So I believe this type of approach of doing model inspection, doing analysis of the subgroup performances is important to reveal and identify maybe whether unwanted information is being used. Now, what we haven't solved at all, and what I think is really important to discuss is to better understand what causes disparities in these models. What are the causes, and in particular, what happens when you have mixing effects, when you have multiple sources of bias. We need to understand whether, or we need to study whether there's methodology that can prevent us, that can prevent models from using unwanted information. There's a lot of that type of research going on in the space of fair machine learning. But more importantly, we need to understand when such methodology can or should be applied, because I'm also convinced that there are scenarios where you need to be very careful about applying, for instance, adversarial training to tell a network to not use certain information. That might actually sometimes make things worse. So thanks very much. I hope we still have enough time for discussions.
Thank you so much, Ben. This was great. I have so many questions and comments, but I will try to constrain myself a little bit. So people can now start posting questions in the chat if you want. And I will also enable all of you to unmute yourselves. So you can also just unmute yourself and ask a question. But maybe I will start with one or two questions, and I will try to make them reasonably short. So maybe you can go one slide back to your conclusion. So you say that there is a risk that protected characteristics may be used. I mean, if there are base rate differences between males and females or different ethnicities, is that a risk, or is that something that we want to do? I mean, if we want the model to learn that it is simply more likely that a female has a certain disease than a male, isn't it actually the right thing to do to use that information?
I think so. and I mean, it's a very, very interesting and probably lengthy discussion we can have about when should we use information and when should we not use. And I'm not sure I'm the best person to answer this, because I think a lot of this goes way beyond my understanding of medical practice and biology in general, and when we need to consider differences in biology and genetics and in general, how disease manifests in different groups. I think this is why I put the very last point, is that there is a risk, and I do see that risk with reports that are just saying there's a bias in the model. I think that alone is such a difficult thing to say, because we don't know exactly what causes a bias. Is it a wanted bias? Is it an unwanted bias? How does model bias relate to data set bias? I mean, all of this is never detached from the data that we use, right? And is the data representing what is happening in the real world, or is it happening because we have already unwanted biases in the data? So yeah, I mean, it's a great question. I don't have a good answer to that. I'm pretty sure there are cases where you explicitly want to use certain information. There are great examples out there. I mean, we know that, for instance, simple things like pulse oximetry works very differently in different skin tones and in different subgroups. So clinically, I think very often doctors are aware of that and might already apply certain, maybe different thresholds on certain measurements to make clinical decisions. The question is, what is this based on? Is it based on our beliefs? Is it based on empirical results? Or on, I mean, I think there are great papers talking about the use of race as part of medical decision making. But yeah, I wouldn't even try to give a complete answer here.
Yeah, it's a complex issue. Yeah. I have one more question. Maybe you could go back to one of your receiver operating characteristics where you showed these area under curve values and the true and false positive rates. Yes, one of these. So, I mean, you had many of these graphs and they always looked kind of similar. And then you said that there were performance disparities because there were differences in the true positive rate and false positive rates, but the area under curves actually look very similar. So my question is, like, isn't this essentially just a model calibration issue? Like, I mean, it looks like you could achieve very similar true and false positive rates for all groups if you like adjusted the threshold. And so that seems to point that the model is just miscalibrated for some of the groups. Might that be the problem here?
Yeah. Yes. And if you look at an older version on our archive, we did have an experiment there, which we still feel very uncomfortable about. But I think it's a discussion we should have. Is for instance subgroup specific threshold selection. So my point is here this operating point, this threshold, has been chosen by going over the entire patient population and say what is the point where we get a 0.2 false positive rate. But given all the differences between subgroups, I mean, there's no hope that this threshold will apply across different subgroups. The question is, how do you choose subgroup membership if you go to something like group-specific threshold selection? Certainly, you don't want to use protected characteristics such as self-reported racial identity to say, oh, for this person, because they say they, on a questionnaire, they had ticked a certain box, you apply a different threshold for clinical decision-making. That's not the way to go. So there's rightful criticism about using group-specific threshold selection, but it is, to some degree, a model calibration issue. Having similar AUCs across subgroup means, in theory, your model is able to perform the task equally well, like well meaning same TPR, same FPR, but at a different threshold. Why is the threshold shift happening? Is one big important question. I think we shouldn't use group-specific thresholds if we don't understand why the threshold shift is happening. But I could imagine that there are scenarios where you do want to change the threshold if you know why it's changing. And I know, or people in machine learning know, that, for instance, prevalence will cause threshold shift. Right? So if you have prevalence shift between deployment and between development and deployment stage, you might have to adjust your threshold. That's, for example, already happening when you train a machine learning classifier, let's say on balance data, and you know at deployment at test, you have a complete different disease prevalence. You adjust, your threshold is not 0.5, right? It's somewhere else.
Yeah, that makes sense. Thanks. Okay, now we have 3 questions. So maybe Orsa, the seminar room, do you want to start?
Sure. Thank you, Ben, for a really interesting talk. I have a question about where the bias comes from and whether we can even measure it. Because if you assume that the bias comes from, the bias in the doctors that diagnose the disease, then you have label noise, as you also touched on earlier. If you have that label noise, or maybe it's not like noise, maybe it's not completely random, but you have some label errors. How are you going to detect your bias? Because your algorithm is then going to be trained to reproduce those label errors, which might actually lead to you seeing an inflated performance on your test set where you compare to the similarly biased errors. So I mean, when you now see a poorer performance on, I think maybe is it black males where you perform a little less good? Couldn't that also be because the algorithm does really well, but the test labels that you compare to are incorrect? Couldn't that also cause this?
I think it's a major dilemma. And we have a little commentary out there on archive, which I'm happy to share, where we're exactly discussing this issue, saying what can we say about algorithmic bias if we don't know what the data set bias is? And the sources of bias, if we can't, we cannot disentangle them. So you're absolutely right. If you make an assumption, I think the important thing is we have to be much clearer about our assumptions in the data, and we have to spell them out in the papers. If you say you evaluate a model and you want to detect bias by looking at increased false positive rate, you make an assumption that your labels are correct, because otherwise your false positive rate is meaningless if there's label noise, right? So if you make the assumption that your labels are correct, then you can ask another question: where's the model bias coming from? Because if you split your data randomly into training and test, you have the same bias at training time and test time. So either you have to say, or maybe there is underdiagnosis, for example, right? And that is, as you say, it's kind of a systematic label noise. It's a really bad label noise, meaning that it's not noise, it's incorrect labels that you give for one of the subgroups. And your model will learn incorrect predictions for this subgroup. But how do you validate this if you don't have ground truth where you say, now I have a test set where I can trust my labels to actually measure the performance? I think it's impossible, to be honest. And maybe one of the conclusions should be that if we use something like Checkspert, where we have no way of telling what the biases are in these data sets, maybe we shouldn't use them for these type of studies. Because I mean, how can we disentangle that? Checkspert is interesting if you look at no finding as an example. And they did some tests on the labels. So I didn't say this, but the labels have been automatically extracted from radiology reports with natural language processing tools, which are not that good. And no finding, I think, has had an F1 score compared to radiology performance of 0.7. So there's a significant amount of label noise. So when you study something like this, what do you do with that? I don't know.
Yeah. I do have one follow-up comment, which is, I think for gender, there actually also is noise in the images. It's chest images. Women have breasts, they're in the way. The images are just less good for women. So there you have, I think you almost certainly have noise, or whatever you want to call it, in the images.
Yeah.
I don't know if you have it in the labels. For the race, I don't know where you would expect to find it. I don't know, is there differences in X-ray acquisition? You know, is this adapted to the patient at all? Is there any leeway for it to be worse for one group than for another? Maybe there is.
Maybe there is, and I can't comment on that. The Reading Race paper has some discussion about that. There were some follow-up discussions around whether bone density plays a role here, which affects X-ray attenuation, of course. It wasn't that easy to extract what is it exactly that lets the network make that high accurate prediction. But it must be, because this was done on self-reported identity, which is a social construct, but it's predictable. So there must be a relation to some imaging phenotype. So but I wouldn't know.
I mean, I guess.
But we know from other technology that technology is biased, right? We know this from color photography, where everything was optimized for white population, so that we get good photographs for people with white skin tones. So obviously this is biased. So maybe something similar is happening with medical imaging.
Thank you.
Then there is a question by Munir.
Hi Ben, thanks for the very interesting talk. I think my question is also very open-ended and very much, I guess, a summary of the previous questions, but maybe rephrased differently. So I mean, my main problem is basically, and I was struggling through the whole talk, what is the exact definition of a model using protected variables? Can you somehow really in formulas, in mathematical formulas, write that down? And when you think about it, why I'm asking that is because if you just want that your predictor is not correlated with your predicted variables, then I guess that's a mathematical problem, and there are certain, I guess, people who are working on that, and there are some solutions. But then going back to the previous question, then there's some correlation you don't mind, and some correlation you do mind, depending on where the correlation is coming from. So basically, I mean, if the correlation is coming from intrinsic discrimination, where the labels are wrong, then that's the correlation you don't want. If then there could be a correlation because just the demographics of if you strata for correct variables, then you might have different demographics, which we've seen. I think the blacks were younger or something. And that might be a correlation, and maybe that's fine because maybe you just want to predict that younger people get less sick or something, and maybe that's fine. And then the third one, which is that maybe these predict variables really do predict a certain disease because females and males, different ethnicities behave different to different disease. I guess I'm not a medical expert, but I remember some years ago someone, I guess with medical expertise, telling me that there was this problem in genetics where the problems that most genetic research is on genes of white people, I guess mostly Scandinavian people, and people are now wondering whether all the research is true for non-white people. So you have all these problems, and so going back, so what is actually the thing we want to research, or what is it you're trying to find? So because obviously just asking the question, is my predictor correlated to the to predict variables, that's easy. I think we've seen it is. So what was actually the research question? Sorry for the very long.
No, I mean it's that is why we have 4 versions of that archive paper already, right? Because we are circling that point, and I haven't nailed it down. I don't know exactly what the research question is, but I know there's something because of an increased number of reports saying, look, AI can be biased, right? It can make things worse. We have to really look into this, that we're not amplifying disparities. The disparities are there, they are real, right? We see the reports. I mean, there's just a report in England coming out that in the NHS, there is systemic racism. People from certain groups have poorer access to healthcare. And now we are saying, oh, we're training all these new fancy data-driven models on historic data. Let's make sure we are not making it worse. There are beautiful examples out there which actually show that you can make it better. So there's a very nice work by Ziad Obermeyer's team on predicting perceived pain, I think in the context of knee X-ray. And they have shown that if you do the standard approach, you take clinical outcome and you train it on X-rays, and then you predict whether someone has disease. Doesn't work for certain subgroups that still have a very high perceived pain, but doctors are not able to see it in the images. And the reason is because they weren't trained to see for that subgroup the type of issues that happen, the pathological processes. They were not trained to see them. So instead, training an AI algorithm on predicting the patient's perceived pain worked much better across these, was much fairer, more equitable across subgroups. So I think, yeah, what is my research question is to try to understand better what's going on.
Then we have another question by Erik.
Yeah, I'm afraid that this is yet another, not really a question, but more of an open-ended discussion. But I will take I'm old and I'm male and I'm white, so I'll take on the hat of being completely ignorant, just to sort of follow the stereotypes. So what if I claim that since we are, at least in this discussion, dealing with health, I mean, it's not about the surveillance or legal systems or anything like that. So now we are in a somewhat protected world. And if I go to my doctor and I want the best treatment, I would want them to know that I'm male. I would want them to know my weight. I would want them to know whatever, as much information as I can give them. And these things matter in order to get me the best treatment. So then the problem is not a machine learning problem. It's a matter of there are all sorts of protected information that needs to go into the system, but of course it should remain confidential. So actually I'm curious to hear, are there any examples, as long as we stay in the health world, where there's somehow, I mean, of course there's a big problem if you have a machine learning model and it has been trained on a selective population and that gives a poor performance on another population. But that's not really a matter of I mean, that's a matter of making sure that the clinical validation shows where will this work, where doesn't it work. If there's an area where it doesn't work, let's improve it there. So it's not really I mean, of course, it's a problem if you're in that group, but it's nice and concrete in some sense. So are there any, I mean, again, being ignorant, and in this time I am actually ignorant, are there any sort of scary examples of in medical image analysis or in health analysis in general where there's something actually problematic going on, where systems could actually be used to disclose protected information that you would not want the health system to actually already know just based on your health record? I don't know of any examples like that, and therefore my intuition is a little bit challenged to see if there is actually a problem, apart from the fact that if we don't have proper data, then we don't make the best system.
Yeah, I think there are examples. I would have to look them up again. I have seen them. So there are reports. For instance, in the US, there was a system that was being used as a triaging tool, which clearly disadvantaged certain subgroups very clearly.
But that's something you would see in the clinical validation. I mean, again, if you have only trained it on old white males, then it will work best for old white males. That's
unfortunately, it wasn't caught at clinical validation. These are FDA, these are regulatory, these are approved tools that have made it into clinical practice, and the discrepancies were realized while it was being already used.
But again, this is not a machine learning problem. I mean, there are plenty of drugs out there that work better for certain subgroups because that was how they were developed.
So I think that, I mean, that touches upon an interesting question, where whose responsibility is it to look into this? Now, as a machine learner or as a statistician, we might push things easily away, right? So threshold selection. So there are statisticians that are very clearly argue, and I kind of, I mean, agree to some point that threshold selection is not a machine learning problem. We shouldn't, as part of our method development, choose an operating point. An operating point means there's typically it's called a utility function, something that measures, are you okay with that number of false positives, true positives in terms of economic cost, societal implications, clinical impact, and so on. These are human decisions, right? Maybe clinicians together with ethical boards and who else should make these decisions. And you're absolutely right. If you go to your doctor, you're happy to give them as much information as you want. You want them to look at your family history, your other risk factors. You tell them whether you smoke or not, because it all matters. And in that sense, in that protected space, you're happy to provide that information to get the best possible healthcare. But we do know that this is not always how it works, especially now with like thoughts about using triaging tools. Now coming out of a pandemic, I don't know how it is in Denmark, I don't know how it is in other countries, and in the NHS in England, we have a massive backlog of patients who haven't seen a doctor. So they are thinking about using technology to prioritize who should now get the precious appointments to see a doctor most urgently. And if you now use automated tools, maybe you even fast track some of them because you have to work through that backlog. Maybe you use a bias tool that actually makes clearly disadvantages certain people. There was an idea in the US after the pandemic for screening, breast mammography screening, to increase the age. Because the idea was younger women will be less affected by breast cancer. So let's increase the age for a few years to just work through the backlog and make sure that people get screening again. It turns out Black women have the highest prevalence of developing breast cancer in younger ages than other groups. So if you increase the age for the entire population of saying, no, we're only screening a certain number of up from a certain age, you're clearly disadvantaging a certain group. So yeah, so it's very difficult where are the responsibilities. I think as machine learning researchers, we should look into what we can do, but I'm also, I think also alluded to that, is there are also limits what we can do algorithmically. And I think that is what the whole fairness and machine learning community struggles with, is what can you do in terms of change the mathematical function and suddenly your system is fair? Maybe that's not that easy.
Okay, I think we can have one last question and then we should close the discussion. I'm sorry. Lou raised the hand for quite a while.
Hi, thank you. First of all, thank you for this nice and interesting presentation. I have a question about the bias you mentioned. I'm thinking instead of detecting the bias and let human to decide if this is wanted or unwanted bias, do you think it would be more beneficial that we optimize the model for the highest performance and let the model explain itself what sort of information it has been using to optimize? Do you think it would be a more beneficial way of doing things?
No, I don't think so. I mean, the highest performance is not necessarily the best target when it comes to equitable performance and removing disparities. Again, it's context depending, I think, and it's not easy to say what is the best objective function to optimize for. I mean, there is this whole debate about does fairness conflict with performance, right? And there are arguments for and against. And I think every other month you see a paper arguing that actually there is a balance to be found between fairness and performance. And then there's another paper saying, oh no, this is all nonsense because you're using the wrong definition of fairness. Actually, there is a way of optimizing both. And I think the question is, it comes down to definitions, like also mathematical definitions of fairness. There are so many and so many different ways of looking at it. I think I cannot answer that question fully, I'm afraid.
Yeah, thank you anyway.
Okay, I think we have to close the discussion here in the interest of time. So sorry, Joachim, maybe you can pose your question like after we close the seminar or in an email.
Send me an email.
Yeah. So let's thank Ben again. Like this was really great, I think. I enjoyed it very much. And then thank all of you for attending. And I hope to see all of you soon in the next seminar installment. Ciao.
Thank you very much.